So I want to start with a motivation, which was a coincidence with the offer that we can do the meetup here. So I did some work which is related to the topic, so to retro computers. And so I have my Commodore here in front. So it's a real one. Everything is real. Everything is, it's not fake. There's no video, right? So it can break. We will see how it goes. And you can see here it's a real 64 Commodore, and I can load the agent. So it's a real agent running on the machine. Who knows OpenClaw here? So basically, this is a Claw re-implementation in assembler on a Commodore running here on the machine. And so it's running already. You see in the top right, there's the Claw icon, a small sprite, and you will see it will do some motion and when it's receiving data. And because an internet, the Commodore cannot connect to the internet, I have a serial line, and you can later on take a look here, serial RS232 line to the Mac. The Mac is just a proxy to the OpenAI API. So nothing is really happening here on the machine. Everything is on the Commodore. And so I have to start this proxy thing. It's called a bridge, and it's already up. And it's connecting here to my phone, so it has a signal number. So it's on signal, the machine. And yeah, you have to trust me. Here's the Commodore on my signal. And I can say something like, hello, Offenbach. Or say, hello, Offenbach. Say, hello, Offenbach. And it sends, and you're already seeing there, it's transmitting something. And I go here to the log. You will see the first thing it's doing, it's transmitting the soul, like the system prompt basically, to the bridge to send it over to OpenAI. So you see 12 chunks of data. It's a 2,400 baud serial line. So it's 300 characters per second or something. Takes some time. But here you see now in the last line, it has sent something to OpenAI. And it got something back. And still working.
Hello, I'm ready.
And everything is on the machine. I have to admit, like the speech is on the Mac, it's just a say command, right? But it's coming from here. This is orchestrating the whole process. And it's magic, right? This machine is from 83 or something. The machine maybe is from 85, but in general, the Commodore is from that time. And I can say something like, who is president of the United States? So I send the message, and if we are lucky, we get an answer in a second. I got motivated by this, and this reminded me also here of the retro park.
The president of the United States is Ronald Reagan.
So, and we tried earlier, test all the knowledge from 83 or something. All right, so I got triggered by this posting here on LinkedIn. Somebody was super proud to have OpenClaw running on a Raspberry Pi 8 gigabyte. And I was thinking, okay, this is not what you need for such a thing, because it's simple. And you will see in a second why it's simple to run an agent like that. So I started this Claw64 project. I used my codecs and Claude subscriptions during KubeCon. Just let it do its job, and it was programming here. Everything is assembler, of course, must be very small. The machine is small. Of course, first question is, where do you put it in memory, right? So you have 64 kilobytes, but there's stuff around, like the kernel is overlaying the RAM, the basic ROM is also overlaying the RAM. Here's some space, but this is used by BASIC. And the system prompt is already something who can calculate 8 kilobyte or something. Is this correct? No. 8 times 250, no, 2 kilobyte, I think. 2 kilobyte, so, but it's still something, right, in this dimension of a C64. So you have to think about where to put stuff. So it's not so trivial. But the idea here is this is an agentic loop. And agentic loop is basically something like that. It has a way, it has an idle state, like at the moment, nothing happens. But then a message can come in. So a message comes here from the user, from my signal. It will receive it, and it will send the message over to the model, to OpenAI in this case. So there's an API, and we will see it later on in the talk, where we send the message. And I talked about the system prompt, the soul in the beginning. Basically, it's telling the GPT model, you are a Commodore 64, you are living in 83, and so on. Like all this information, meta information. And when you send the message here, like say hello to Offenbach, or who is the president, this is basically appended to this system prompt. And OpenAI will answer. So this box here will basically send the request to OpenAI. It's here at the bottom, and eventually an answer comes back. And the answer can be multiple things. And this is like what makes OpenClaw special, an agent special. Agents have tools. It's not just a chat, right? A chat is simple. There's just one tool. Send a message to the user. But here they are multiple. So this machine here, it can execute basic commands. So it can do something. Can even speak here to this thing. Set the background color to red. Okay. I have to retype because Apple's voice detection is not good. Set background color to red, and the model knows that it can write basic commands. So in a second, we'll see a poke command. And maybe somebody remembers what the numbers, the memory address was for that. Anyway, there are multiple, like there's exec for basic commands, there's screenshot, you can get the text screenshots. You can ask whether basic is running. You
Background color set to red.
And if we are lucky, it's red. So, and you can even write programs. You can tell it, like, write a program counting from 1 to 100 and run it or something. Has all access to the basic. And one can also build something like memory. You could store something on disk. I haven't implemented that. I have an alpha feature for a heartbeat, so it's every 2 minutes it would be woken up. But we notice there's a bug, so it crashes. So I switch it off for the moment. But anyway, this is an agentic loop. And if you use Claude or Codex, such a thing is running there. And it's not more. And you can imagine this thing can be written in a C64 assembler 2 kilobyte block, right? Or 4 kilobyte block. Not too hard. This is like, there's a message protocol, like it cannot speak HTTP, not TLS, obviously. So this is done by the bridge. But other than that, it's a very simple protocol, and the bridge translates that into JSON and TLS encrypted and everything else. All right, that's motivation. It's magic. And our task today is to understand how this magic works. And maybe very quickly, I don't do the same. So who has been in Heidelberg, by the way? I know, so 3 of you. So I gave an introduction, and I will do it very short here. There is this computer here. It's a Vectrex console, and I heard it's available there. So please take a look. Somewhere there, there is a machine. And the kind of crazy thing is, if you look on the monitor there, and you can see it in a running state probably later on. This is vector graphics. It's not digital. Like there's a cathode ray tube in this device, right? It's like a TV screen. And the computer modifies the direction of the tube. It's not pixel by pixel. Yeah. And somehow in the past, in the last, 50, 60, 70 years, we have learned to do everything digital. And LLMs are basically many roles back. Like we think maybe digital is not the right thing for more advanced computation. So we are doing, in LLMs, we are doing basically analog computing. And I have some examples here, but because we don't have so much time, there have been, like in rockets, for example, in old rockets in the 50s, they used analog computers, and later on they made it digital. But at the time, they had a ground station, which was digital, like normal computers at the time. And then they had the analog computers in the rocket. So that's a division between those two models. And LLMs are very similar, right? Here we have the digital machine, the Commodore, but the LLM is basically an analog computer. All right, so what happens when you say something, who is the president, right? So we ask the computer and send it over to OpenAI. And what happens behind the scenes is basically one service they offer. And this service is called next word prediction. So basically, it can take a sentence and it will return us the continuation. And our running example today is the cat sits on the, and the continuation, the natural one natural one would be on the table. So those LLM models, they can complete such a sentence. That's basically all they do, nothing else. And we are basically mapping everything, like the magic we have seen here with the Commodore, to this simple problem and the solution LLMs provide. It's not 100% correct. If you look more detailed, actually it gives us the next probable words for every word in the sentence. Like what is the probable word after the, can be anything, right? Can be car or house or whatever, but can be cat. What's the word after cat most probable? Sits, or maybe it could be eat, right? Many words. But actually we are only interested in the last one. But the algorithm we will see is computing all of those. And this is waste, right? We don't need those words here. And Chris will give a second talk after the pause, and he will basically talk about this. This is waste, and we don't want to do this computation every single time. Okay, so next word prediction. In practice, when you go to a web UI, like you type something into ChatGPT, the cat sits on. What happens in the background? There's an API. That's the API we are using here for the demo on the Commodore. So we are sending a JSON blob to OpenAI, v1 responses, whatever, and basically the sentence is in here, right? And the model will compute and will give us the completion, the continuation. Behind the scenes, we don't see it in the case of GPT because GPT is closed. But if we take open models, and I have my own model here, and we see it in a second. Actually, like the model doesn't get JSON, it gets something like that. Like there's a start. We saw the system prompt earlier, right? The 12 chunks of some 100 bytes sent to GPT. Like I'm a Commodore, I'm living in 83. This is first sent, then the sentence from the user, and then assistance, or special tokens here. And then the model will complete this one here, like the table in the living room. That's what's happening. And then we see, of course, the answer in the web UI. If we dig deeper into the model, actually it cannot complete a complete sentence. What a model can do, it can complete one word at a time. And to get a full sentence, we have to call it again and again. So basically we are completing the cat sits on then the model says table. So we are feeding the table into the next input. And we ask the model, the cat sits on the table. What is the next word? In is the next word. And then we append in to the input. We call the input a context or a prompt, but context is a normal word. And we do it one by one, and this is what one calls autoregressive, because it takes the output, appending to the input, and continues this loop until some end condition is found. So like the end of the sentence. If the dot is returned, we are finished, right? All right, this is autoregressive. And the solution to this problem, this is describing a problem, right? We don't know how to solve it. And the solution came in papers. But before I go into the papers, I want to start our training. So what we do here, so we want to train a model from zero, basically, from random numbers. So what I did here before, I got a H100 machine, and you see the price here. It costs like €2 or dollars per hour. And you get a SSH login. It's a container somewhere in the cloud. Ours is in Thailand, I remember, right? Because it was the only one available at the time, like half an hour ago. And it's running here. Actually, we lost connection. No. This one, I think. I hope. There we go. So it's not very stable. Let's see how this goes. Oh, we can. Okay, I'm not sure why this happened. So it's called NanoSchnack. It's built in PyTorch, so it's a Python library to build models. And I will not go into details. Chris shows something of that later on. But for now, we are just on a machine, and the machine here you see at the bottom has a GPU. It's a H100 NVIDIA card. It has 80 gigabyte of RAM. 80 gigabyte is 1 million times the Commodore, just as a number. All right, so we have a Python environment again, and typing blind here, so just train. And this should start. It takes time. So I promise most of the outputs, the parameters, you will more or less understand after the talk. So don't be, don't have imposter syndrome. There are lots of keywords, and I will explain lots of them. So LLM is a large language model. And it was introduced by 2 papers, basically. Here's one, the first one. It's a famous Attention is All You Need paper, 2017, mostly Google people, I think. And they introduced an architecture for a neutral network, basically, which had something called attention. Attention is all you need, right? This is the center. This was an invention. We will learn in a second what this is. And this model was for translation. And this was the inspiration for the OpenAI people to cut off the left part here, simplify it, and use it for completion of sentences. And training is done with internet contents. So maybe we see that here. You saw it maybe. Here you see my... So this model is trained in German. So there are databases like 1 million posts from, what is this? I'm not even sure. 1 million posts from, what is it, Reddit or something. There's Wikipedia. There are YouTube comments, like everything German I could find, like a copy of the German internet if you want, basically. And this is fed into the model. The model is trained with that. And our hope is that it will learn German during the talk. We will see. It's downloading and it's feeding the model now with the training data. And the architecture is this from the GPT-2 or 3 model paper. They are basically the same, very similar. Model looks like that, and we see in a second what this means. Steps of understanding. So what we want to do, or what motivated me at least, I learned like programming on the Commodore, and then I went to university, learned it professionally, computer science and stuff. But basically, all the knowledge from the Commodore programming, that was enough. Everything else is just extrapolation. It's the same thing what I could learn in a basic interpreter on the Commodore. And the idea here is, if you understand a model of for Neumann architecture, basically, any modern computer looks more or less like that. Here's the original, like the mechanical computer for Neumann. You can understand how it works and how even like a Windows or a Linux or Mac OS can run on it, right? You can imagine a Linux kernel could run on this machine if you made it 1,000 times bigger. That's all. It's just intuition for us engineers. With those models, we lose that, right? So, and the goal is to regain this understanding. Everything here is about training. So we have a model, we have an architecture, we saw this picture from the paper. We don't understand yet how it looks like. But if you imagine this architecture, and if we put, like there are many, many parameters, we call them weights inside, right? Many matrices. My model has 110 million parameters. If we set them in a certain way, we could simulate an algorithm. So we can do certain things, we can find parameters and imagine if we choose them correctly, it can do certain things. It can maybe multiply. It can understand what a verb is in a sentence. It can understand what German concepts are, like words mean and so on. This is the first step. Second step is if we can train the model and improve the parameters more and more without limit, like it goes down, it's asymptotic, but it's going down all the time. Eventually, this model will learn, right? Those two things, if we believe in them, the model can express something and we can basically improve it. It will reach the state which we tried in the first case here. Then we could have an idea that, this model could actually do that if we trained with German internet data. If you look here in the training, I'm not sure how far it is. Oh, okay. Out of memory. Why? So we have multiple ways. Maybe this was a reason before as well. So I reduce the size of a batch. Batch is basically it's a chunk, it's a blob from the internet. Like for example, I think one sentence is 1,024 tokens. We learn in a second what a token is. Basically, a word is a token or two. And 1,024 is my sentence length, and I have 32 at the moment in parallel. So we are learning from 32,000 tokens in one step, like every line. And 64 was too much. The machine, as I said, has 80 gigabytes. So we will see how this goes now. I hope it doesn't happen again. It's very hard to get those GPUs, we noticed. Like when I gave the talk in Heidelberg, it was easy. You could just choose one. It worked. Now they were like 2, and they were always there. We had to wait until another one turned up. So it's tricky. So maybe this one is not stable. Could all be. Anyway, so back to the theory. I mentioned tokens. And what is a token? A token is a very simple thing, actually. We take a sentence or a text, German text. So geschrieben steht, and you might remember what it was, some Goethe-Text. Am Anfang steht das Wort and so on. We are taking all 2 characters in this sentence and count. And we will find out that CH, like the combination CH, is most common. Like it's 9 times. EN is 8 times. And we are replacing all CH, like the top one here, with a new token. So the text is ASCII. So it's 8-bit, 256 characters. So the last one is 255. And we assign 256, so one more to CH. So we replace CH with a new token here. And then we do the same thing. We count again. And this time in the text which comes out of that, we are replacing against the top. Top again is, as before, it's EN 6 times. We're giving it also another number, 257. And we continue that. And you can imagine we do that, how long? We did that 32,000 times. Like we always reassign numbers to longer and longer subwords, like combinations of characters. And after 32,000 times, using a 1 gigabyte of random data from the German internet, you get basically that. So geschrieben are 2 tokens, right? G is 1 token, so it's a 21,736. Rieben is another one. And shorter words, which are more often in the context which we use for training, hilft is 1 token, right? Shorter words in German are their own token. And this is what is called tokenization. So every sentence which, like the cat sits on the, right? This is first tokenized. We use the tokenizer, like this mapping to those subwords, and create those syllables, like and get a stream of numbers. And it turned out during training, this is better for an LLM if you have this input here than having ASCII characters. Because here in those words is meaning already. So the LLM will learn what those tokens mean. And GPT-2, this is my the inspiration for my model. Mine is very similar, not the same. They use a different tokenizer because they trained on English data, not German. So they have different numbers. And every model nowadays has different tokens. Modern models, they have many more tokens than that because they need tokens for all the languages in the world, right? GPT is trained on, 120 languages or something. So they have tokens for everything, basically. Ours is German only. And you can imagine a German tokenizer is better for our use case, right? If we want to train, die Katze sitzt auf dem Tisch im Wohnzimmer. If we use the GPT-2 one, like the English tokenizer, we get many, many more tokens. And if you use Claude Codex, like any kind of coding agent, you pay for tokens, right? So more tokens is expensive. So a better tokenizer is very important here. All right, and now the first intuition comes. I said models are analog computers. Who has done linear algebra in university or in 11th grade? Everybody, I guess. Yes. So here, it's a 3-dimensional vector space, right? Every token is represented during computation in a model with a giant vector. Not 3-dimensional, but in my case, 768 dimensions. So 768 of those arrows here, basically. Every direction is a real number, and very big vectors, like very, very, very long, 768. And the first intuition is, why are they so long, right? We have 32,000 tokens, which is 15 bits, right? 15 bits are enough to encode 32,000 tokens. So if we imagine a vector encodes our tokens, like for every token, we have one vector. It would be enough if it was very short, like 15 dimensions. But it's much longer, right? So we have lots of space here, and space is something like memory. A computer like a Commodore, 8-bit, right? It has registers. There's an X register, Y register, accumulator. All of them have 8 bits. Those words here, those tokens, they have 768 minus 15, which is 753 of space, basically, which is okay. Very important. Those vectors here, they are learned in training. In the beginning, they are completely random. So in our model, we can take a look here. It's learning something, and it's already speaking something. Oh, okay. This is already a half an hour old because we started half an hour before the talk. So it learned already for some time. So it learned on, where is the token number? Here. So it has already 631 million tokens processed. Quite a lot, right? And you see here, it already learned German to a degree. So here you can see it's completing something. It's not super intelligent. If you ask for the meaning of life, it will give you something. Maybe it will mention meaning and humans or whatever, but it will not give something coherent. This is getting better over time. And what we are looking here, so we talked about training, right? Training means some value we call loss must go down. And it's going down, hopefully. Yeah. We restarted. Because we restarted, we didn't start at 0. So that's a pity. Otherwise, we would have seen the curve went from, I think, 12 or 13, which is the theoretical maximum, down to 3. And if we leave it running for a few hours, you will really see a slowly decreasing curve. When you do training, you're a research scientist, right? You're working at GPT or at Mistral or some other company. Those people will watch this number. Like they will wake up in the night, take their mobile and check this number. This is basically the meaning of their work. This has to go down. If it goes up, they have done something wrong, and the model is not improving. So remember, we talked here about what we want. We want to learn, right? We want to make sure we can, here's a second goal. We want to converge. We can learn against the German internet data. If it goes up, that's a bad sign. Yes?
Can we ask questions?
Yes.
When it says loss 3.8, what does that mean?
We see that.
Okay.
It comes. Here you see the slides already, so comes in a second. So anyway, what I want to say, we are training, and those vectors here, basically we take the cat 3070, 197. What this vector is here in the vector space, this is trained, it's learned. And if we do that, and we use those tokens and the meaning, you will see like certain words, those which happen more often become, have small numbers, right? Longer words, if they are more often, like Deutschland, of course, is very, very common in German text. It gets a number. Frankreich is a bit less, so it gets a bigger number, right? This is what we have seen. There are longer words here, Donaudampfschifffahrt, Gesellschaftskapitän, and those things, they are giant numbers because there's not so much text about that. But was there also 2 tokens. But what is interesting, those tokens have meaning. Tokens and the vectors. And here we see just pairs. Berlin, Hauptstadt, Deutschland, Frankreich, Vater, Mutter. Like words which have some similarity in some sense, like in a semantic sense. And they are vectors. And who remembers scalar product? Dot product in English. Scalar product was 2 vectors multiplied, every component and summed up. If the number is big, the vectors are similar. Like they are not orthogonal. This was a typical example at school, right? Orthogonal gives 0, but if they are like a similar direction, they get a big number in the dot product, in the scalar product. And you can already here in the training, you find out that if you take the dot product between those 768 dimensional vectors, you can compare them. You can say Berlin, Hauptstadt, it's a big number, it's 8. Deutschland, Frankreich, it's a big number. Hundzug is a very small number. because there is no correlation. I mean, not much at least, right? And you can play games, right? Lehrer and Bier is also small. For whatever reason, Vater, Wiesbaden, whatever. I took random numbers here. So the model is learning those token vectors, and they become very rich. Like they are like a dictionary explanation of words when you look them up for German words. Yes.
But doesn't a big product not only mean that the tokens often happen together in sentences?
No. We will see how we train. Maybe this gives you some intuition why this happens, because it depends on what we train and how we train. And you can, I show that maybe a bit earlier, you can even do something, you can do mathematics. So this is hard to read, I'll make it a bit bigger. So you can say something like Vater minus Mann plus Frau is Mutter. So you can just take the vectors 768 dimensions, you do the subtraction addition like you did at school or university, and you ask what the result is, and the result is very similar to mother. You can do that. So those vectors become really carriers of knowledge, of semantical concepts. That's the idea. And if you see here, I find this impressive here. Dresden minus Sachsen plus Hessen is Wiesbaden. So this means that in the word Dresden and Sachsen and Hessen, the word Wiesbaden is encoded. They're all correlating or interdependent, kind of. In the word cat, there will be the concept of eating, sleeping, sitting. Those things are encoded in cat. That's the idea. And dog. What? All right. So
you didn't actually, also in Heidelberg, showed how these embeddings, these vectors are trained.
Yeah, so they are trained. They are part of the model. And maybe, this is a good, so maybe I can go here, just very briefly. Or maybe not here. I have a special one, if I find it. I think it's this one. No, not MOE. This one, I think. So this is a model, and the cat sits as input, 3 tokens, right? And here at the bottom, you see it's basically a lookup table, 3 of them, 3 lookup tables, all the same. A token comes in, and it takes the 10,718th column in this table, which is here, and converts or selects basically that vector, and the vector comes out, which is for sits, it's this one, so it's the right one. For it's the left, and cat is the middle one. So, and this is part of the model, right? The model is basically drawn here with not much detail, right? The transformer blocks are not explicit, but here are many, many numbers, many, many real numbers, and they are trained. Part of the training. How it works comes now. And at the end of the day, we are computing the result, we are computing the completion of sits, right? The cat sits, and the completion should be on. So in the computation, everything which is here, very briefly, the tokens go through as vectors go through. Eventually you get a vector here, and this hopefully is on, the vector for on. And then we take the same lookup table and find out on is actually the token 70 or 178 or something. So they are part of training. And training, so intuition about training. And we mentioned already loss is important. So kind of going down, but we are already pretty much in the training, so this takes a long time. The estimate is it takes 2 hours until we have trained 20 times, like the input size is 20 times the model size, like 110 million parameters. So this is a computation until we have roughly 2 billion input tokens as training data. So we take 2 billion tokens of internet data, German internet data, and feed it into the model and compute loss. And this is what you ask about, so let's go into that. So training. The model we have seen, like this architecture we saw with those many boxes, there are many, many numbers inside, right? Many, many matrices. And training means we take the model with the numbers we have inside, right? The numbers we have here now. We apply it to a sample. This is just internet data from the German internet. We compute the model, like we make one forward pass, that's how one calls that, like we run it one time. We get all the completions, of all the words. That's what we showed earlier, right? We get all of them, not only the last one, all of them. So maybe car eats right. Eats is good, right? Right, well, it's okay. Car is not what we want. We are computing again in the vector space, like we use those token embeddings, like long vectors, and we compare them to what we actually want. Actually, we want cat sits on, but we got car eats right. We take the difference, take the length of the difference. This is here the difference of those two completion, or the completion and the data we see in the internet. Right? We have internet data, so we know what is the completion. That's why we need this giant database of internet data. And the length of this vector is L. This is the number which we see here. So the distance now is 3 dot something, and it should go down. And training means we have to adapt, we have to improve our metrics. And we can do that, and I showed in a second, with a method called backpropagation, gradient descent. What it actually is, everybody knows from school or university. Like here's a quadratic function. Here's our sample which we actually want, like the real completion we are looking for. Here's the one we compute. Like this is car sits right, was the completion. This is cat sits on, right? So we are not too far away. It could be much further up, right? The distance here is basically the L, the loss for our sample. And now we can do something. We can take the derivation. You remember derivation, like Kurvendiskussion at school. So we take, for every parameter in the model, we take this slope here. And for computing the slope, you need something called Ableitung, derivation in English. So we compute that, and if it goes down, we know we have to move to the right. If it went up, we have to go to the left. So imagine we came out here, slope would be positive, which would mean we would go to the right, to the left. And we are doing that for every value in the matrix, in the model. So going back here to our architecture we showed here. Here are 100 million parameters. And we do this computation for the cat sits for every parameter in the model. And this is what the GPUs, like the adapter we rented here, is doing. So we rented a GPU, $2 per hour roughly, and we are using that to compute exactly the derivations and to update weights. This is happening here. Where is here you see 250,000 times a second. That's training. That's all it is. If you look on the big AI providers like OpenAI, they do that, of course, in different dimensions. They don't have 100 million, they have like billion or trillion parameters. Yes.
And how is in a big model training the targets tokens chosen?
Same thing. They take the internet basically, plus a lot of synthetic data nowadays, and they do the same thing. So I have to find my here. So they are running the model. So basically, they are doing that with the input from internet, right? So it's not cat sits on. They take random sentence from the website of the retro club here, right? Okay. And they compute it. They compare how far is it away from what you want. Takes the derivations, the mathematics about the matrices, how to adapt them. Do that. Takes the next chunk. That's all it is.
So without waiting, whatever is most in the internet has the highest probability.
Yes and no. It's learning things which are more often in the internet. It learns it better. But it's not just remembering. So, and I like this tweet here. Not this one. No. Yeah. So it's even, right? Even numbers. So you can, of course, write a function which looks like that, and then eventually, is there a better way, right? And he figured it out. So he takes the word as a string and takes the last character. So this is not what models learn if you don't overfit. If you don't train too much, you can train too much. Like the small model cannot train on the whole internet. It will become like that. We don't want that. If you stop early enough, you get that. That's the trick that happens. Generalization is what this is called. And we want, of course, this. We don't want the upper one.
In your example, you had the test function is, what was it, the Hauptstadt von Deutschland is, yeah. What if you have multiple tests? You only do it with one? If you do multiple tests,
I do it in my model. I take 1024 tokens. So I take the whole internet, I stream it, the German internet, I stream it. I take always 1024. There can be overlaps between websites, like website stops, the next one starts. I just take that and feed it into the model and do this loss computation I showed.
You do it for everything?
Yes.
Okay.
Yes.
This was just a sample for you.
And about your question about what is often in the internet, right? In the beginning, I was only using Wikipedia. And the model, when I was asking something, the style of answers was always like Wikipedia. So it's adapting the style. Then I was thinking, okay, there's so much YouTube comments, like all the transcripts of YouTube videos in German, right? I took that, and maybe you see the number of rows here. Is this visible? Tokens, yeah, I see it here. So you have to be careful not to have like one kind of data too much. Eventually, it was always answering, like completing, welcome to my channel, because I had too much YouTube inside. So data preparation is super important. And German data is not as good as the English. For English, you get very handcrafted Wikipedia data sets. You don't get them for German.
Isn't it possible to just do a big sort minus u on the data for a specific token length?
To do what?
To unique.
I mean, it's not about tokens. It's about sentences. It's a context. And we come to that in a minute. Attention is all you need, this paper title. Attention is really, it's not about one token, it's about a whole sentence. It's learning concepts from sentences.
Question.
Yes.
Does it improve when you do the epoch? Every epoch you do the
you tend to overfit. You must be very careful. So you can measure how much you overfit and stop early. So anyway, so training. So it's basically that Kurvendiskussion. So you look for where you are left or right of the target data. And what is super important, I said in the beginning, those models are analog computers. Why? Digital computers, digital functions are not uplightbar, differentiable, right? You remember like a function which goes like that. Here you have a point where there is no slope. You cannot compute it. It's undefined. So functions which look like that are much, much better because we have to compute the derivation. So those models are built in a way that everything is differentiable. This is why why analog computers are much better for training than digital computers. And all the formulas you will find, like matrix multiplication, you might have learned how to do derivation at university. The maximum function is pretty common. There's a different name, ReLU, it's the same thing, it's maximum. There's one point which is not differentiable. You can just define it. There's a workaround. You just say it's a half or something. Then you're fine. This is okay. There are some norms, like to norm the length, variance in vectors. Everything here is differentiable. This is how you build models, that everything is differentiable. Because if you do that, it works. And so here's a small snippet of the PyTorch training loop. So in PyTorch, the framework I'm using, very common. It's one of the most common frameworks for training. And what it's doing, it's running the model. So it's going through the model once. This is what we saw in the beginning, right? Every completion of every word, next word prediction. Then we compute the loss, which is the difference between what you want, the green one and the red one. And then PyTorch has like this mathematics of Kurvendiskussion, right? It does it in one call. Like, it's automatic. You don't have to do it manually. There's a backwards function, and this changes the weights. And this is a loop. This loops like 10 billion times. This is what we are seeing here. Nothing else. Super simple. I mean, the mathematics is simple. That it works, of course, needs intuition, and that's the next thing we will see. So before we go on, a last thing. Why doesn't it happen? Like when you know from school, right? If you do this, this is a local minimum, not good, right? There might be a global minimum much further down. So why doesn't this happen? And of course, in 3 dimensions, you can also imagine there might be local minima where you can get stuck. And the intuition is if you like in a 2-dimensional space, probability that you get stuck is still pretty high, and you might remember there's something called a second derivation at school, and then you can say something about negative and positive, and then you know whether it's a minimum like that, or it's actually something which is called a Sattel in German. And the higher the dimensions, and the less probable it is that you stay in a minimum. That's why. And we have millions of dimensions here. 100 million here in my case. So it's very, very improbable that this happens. But it can happen in theory. All right, so architecture. So we are here in the Retros park for computers, and you remember that maybe. Some of you might have learned that at school, like Gatters in German, right? This is a binary adder circuit. Imagine a model is something like that, but the connections are random and they are changed while training. The gates are fixed. The gates are what you build into your architecture, but everything here, everything else, the connections are trained. They are disconnected or randomly connected in the beginning, and while training, they're getting more and more in the way you want it. Like when you train to get a binary adder, they will become like that, right? And you can do any kind of complex things, flip-flop, you remember that. And you also remember, so we talked about how there's space, right? Space in vectors, which is unused. Memory, lots of it. Okay, so what we have seen, I have to go back. We looked at this already, right? We have this lookup table, mapping the token numbers to vectors and mapping vectors back to token numbers. So those blocks we have more or less understood. They're just tables, nothing else. A model, maybe you have seen that. Where could I show that? I think on my screenshot here you saw something like temperature. Here in the OpenAI, no, it's not here. A temperature is basically, a model is deterministic. If you put in the same input, the cat sits, it will always give you the same output. If you take the most common, the most similar output vector here. But you don't have to do that. You could do sampling. You could take the most common, maybe the top 10 tokens. So for example, the cat sits on the completion is table, chair, floor, and 7 others, right? We take the top 10, and then we take a random selection of that. So we have some probabilities here we can compute, and like here, and we take one of them. And maybe table is the most common, maybe car is less common, but sometimes cat sits on cars. So maybe here is the car, and here is the table. And we take a random one, but following those probabilities, and maybe table is the most common, so we get table. But we can randomize, and this is called temperature. But the models themselves, they're actually deterministic, like the mathematics is deterministic. So we have understood this. We have understood how to find the tokens again. There are a couple of norms, and norms are a frightening thing, but they are actually pretty simple. So imagine we have something like a cat, but the vector is kind of degenerated. It's very much negative, but looks still similar to a cat. So this is also a cat, right? Maybe it's rotated, or maybe all vectors are half the size. It's still in the shape of a cat, but somehow degenerated. And you can normalize it again to be like the average, the mean value could be 0 again, and the divergence, variance could be 1 or something. So this is layer norm. You do that for stability of the model, not super important here for our learning. And then we have transformers. And transformers, so attention is all you need is a paper. and it introduces transformers. And this is what we want to learn here now. All right, so I unfolded here a transformer block. So you have blocks here in the model. And in my model, I think I have 12. Yeah, I wrote it here. 12 blocks which look all the same. So all those, resolution is not very high. All those blocks here, they are all the same. N times, 12 times in my case. Modern models like GPT-5 or DeepSeek version 4, like the latest one, a week old, has 100. 100 of those blocks. And again, we have norms here. Forget about the norms, they are boring. If you remember, so who has done neural networks at university? Like old style neural networks. This is a normal one-layer neural network. Very simple. And the activation function inside is just the maximum function. So it's a super simple neural network. The interesting bit happens here in the self-attention, in the attention block. And this is what we want to look at now. So to give you some intuition. Okay, so attention. There are some predicates like this. It's called causal, it's called self-attention, and it's called multi-head, actually. So there are multiple things, and we will see what it means. So everybody knows that, right? This is a CPU, like in the Commodore. And there's an ALU. So ALU computes, right? Can do addition, can do OR, and all the operations. Attention is everything which is not the ALU. Everything which is about shifting data around. Like there are registers, moving data into registers, between them. This is what attention is about. And why is that? If you look in the model, in this one, and this picture you don't find in the literature, but I like it because it explains one thing which is not so obvious. The cat sits as input, we get the embeddings, so we go from tokens to embeddings, we do some norming. And you see here, every token and every of their embeddings goes through the network in parallel, with one exception, attention. But if you forget about attention, everything is parallel here. And you can imagine a GPU, like a high-performance CPU, which can do matrix multiplication very fast, very parallel, is perfect for that, right? Everything is parallel. I can fed in 1,000 tokens and do it all in parallel. The only exception is attention, because attention is moving all data between tokens. That's why it must be across words. And now we see, so this is your question from earlier, basically. Here's table. And table can learn the concepts of its context. The table here it has an article. This is not very interesting, right? But there's on. Table learns about on. Like something is on itself, right? Table learns about something sits on it. Eventually, it will also learn a cat sits on. So the table token, you remember there's lots of space in the embedding. All the space, the memory, is extended with knowledge from everything before. Yeah.
But you wrote an arrow with casual from left to right.
Yeah.
Is general because in some languages the casualty could also
No,
be from the right to the left.
Yeah, and this I mean, this is true, but eventually, like there are many layers, it will also get the data around. But it's basically because where's the yeah. This is how we train, right? We inject a sentence from the internet. We compute the next words. If the network, the attention block, could look forward, it could basically peek at the next word, at the next token. So it would not learn. So we have to restrict how it's doing attention to everything before. Otherwise, it would not learn what the next token problem is. This is why, because we do that, because of causal, we are learning the next word.
And why not just give it the sentence, the cat empty on the table?
Because you don't know, I mean, you have 2 billion tokens, it's like 6 gigabytes of text data, right? What should you don't understand the sentence, just ASCII text. What should you do, right? next word is just so simple that you don't have to understand the sentences.
Okay.
And because we use this causal restriction, it never peaks at the next word by learning the next word.
Mm-hmm.
The only data it has is everything before.
Okay.
And what it looks for, like the intuition I gave is that table learns about sits, on, the, and cat, right? What it learns is encoded in weights. This is just our intuition. It could look in front and get the semantic meaning. But it could also look on just like if there's a color, like black table, red table. Maybe it looks just for color words, right? Or it could look for, I have some examples here, word order, subject-verb relationships. And we don't know. The model learns that, right? Imagine, remember, we are here, right? We have random and then trained connections. So how it uses this power here to learn from the previous words, it's totally up to training. We don't know. But it could look on certain things. And this is encoded in basically, the idea is the following. Imagine table looks for what sits or what is on it, right? This is the goal it wants to train to learn. It will create it's a query. It's a bit like databases. So there's a Q matrix which turns the table into some other vector which encodes what it wants to have. Every word offers something. We call that key. So it's every word, for example, sits offers I'm a verb and I'm about some action of a human or an animal, right? And query and key are compared. Again, dot product. So you can take the dot product. If they are similar, then information flows. Those are the arrows here from sits to table. And those here, there are matrices which encodes this basically this database query, key, and response pattern, right? Q, K, and V. And Chris will show that in his talk. There are many of them. And if you look on the model, we said we have 12 layers, 12 transformer blocks. In every of those, we have n heads. So basically n parallel attentions. They can all look on different things. So we have, I think there are 128, if I remember right. So roughly 1,000 of those operations happen here. So different operations sending data from the previous words tokens to the token attend. And the model can learn 1,000 different aspects of words this way. Yes.
This looks for me, it's like parallel computation in causal, but in another dimension.
Yeah. So, the query, key, and value analogy. If you take that, and now we have many words, right? We have a long sentence. The cat sits on the table. You compare basically every word with every other word, whether it wants to send data. So you get a matrix, and the matrix is quadratic. And everywhere where the box here is dark, a lot of information flows. If it's light or empty, there's no information. Like the article "the" doesn't get anything from cat because it's unrelated in the sentence, right? But basically, this is what has to be computed for every combination of tokens in a sentence. And if you use Codex or Claude or something like that, and you remember there are context lengths, right? And nowadays, those sentences, they are not like 6 words, or in my example, 1,024. Nowadays, they are 1,000,000. This matrix, 1,000,000 times 1,000,000 is in a dimension, right? This cannot be computed by any machine nowadays. So a lot of effort goes into making this faster. And one intuition here, and this is basically the core idea for, now we come to Kubernetes. Why is Kubernetes matters here? When you want to run those models in Kubernetes, computing this matrix here is super expensive. It's just too expensive. But there's one insight. imagine we start with the cat sits on the table, right? We compute the next word, which is in. And then we remember, we append the in to the context, autoregressive again, and we run the model again to get the next word, the living room. The matrix here only gets bigger in a linear way, right? You see it. Every step, everything from the past we can remember. And if you look on the formula, I don't do this here in detail, but in the formula to compute that, we can remember the K and the V value for the old tokens. So every time we complete, we have KV cache. We have a KV cache in memory on the card. We don't have to recompute everything again. So if you want to run that, and Chris will show that, everything is about having a KV cache and using it, reusing a cache. This is everybody in AI thinking about to make this super efficient. All right. I think we have seen most of it. And maybe, yeah, I go back to this example. So we have seen in attention that the words learn from the words before in the sentence. And then you can imagine those words, when they are training, they get more and more information about how Dresden is used in a sentence, right? Somehow Dresden is used in the sentence often with Sachsen. So it learns in the space of the embedding vector, so empty space, it learns that Sachsen is somehow related. It stores this data that Sachsen is a Bundesland of Dresden in the embedding. And it even learns between the different Bundesländer here that Wiesbaden is in Hessen and so on. So this is all encoded and trained because attention learns the context of sentences. And nearly a last thing, if we look back where we started, we wanted to get an intuition, right? And we know we have this data transfer and attention, so we can pick semantic meaning in the words before and copy them into the words later and enhance those embeddings. And I don't do this here, but you can make up examples where you really compute something like, I have one example, maybe very, very briefly, where you compute. So you are computing the complementary color of lookups. You make a lookup table basically of complementary color with those mechanisms. So you can encode them and really give numbers like real matrices to encode certain tasks. And you can do that for other things like what I had here. Where was it? Here are the examples. You can encode them. This is basically the architecture can encode certain algorithms. And this is the first part of the steps of understanding. Like we can encode certain behavior, certain semantics. Second part is learning works, right? And learning works is mathematics, Kurvendiskussion, derivations. And you are seeing here in our example, it crashed again. This machine is not good. And a machine costs a few euro per hour, right? But if this happens in your night while you are sleeping, you wake up and you have paid 6 euro per hour and it was staying there for 8 hours. But it's just a small model. If you have a big model, it's of course even worse, right? But we can go back here and just look on one of the sentences here. Die Hauptstadt von Deutschland ist mit, okay, it's getting the idea that Hauptstadt is something with, and Stadt has Einwohner, right? Population, größte Stadt. It's getting German, obviously. It's still not the real thing we want. But if you look where we are, we have trained with, where is it? Not even 1 million tokens. So we would train a lot more than that, 1,000 times or so what we have now. All right, and here I didn't say that. Another goal of the researchers is to keep this line here at 100%. If it goes down, you're wasting resources. So optimizing that is also a thing, and Chris will also talk about that later. In inference, same problem, keep GPUs busy. This is all you want to do. And not everything here is new. There are lots of YouTubes. And I want to just highlight here Andrej Karpathy. Maybe you've seen this name already. He pioneered to brain dump everything he knew about or knows about LLMs. And there are like 20 hours of videos from him. You will understand a lot what he's talking about after this talk. Please take a look. And the last thing he was doing, or one of the last things, all the mathematics we have seen, everything of training, the PyTorch training, the PyTorch code, but now written out in primitive Python code is on the slide. I mean, the resolution is bad here, right? But everything here, this can be run on your machine, on a CPU, has everything to train a GPT-2 model of the size which I showed, like 100 million parameters. It's not fast, there's no GPU acceleration, right? There's nothing which parallelizes. But this is all that powers AI. Like, I don't know, 300 lines of code or something. I cannot read the number anymore. 200 something. This is all the mathematics and all the code. All right, I think.
I want to go back to the embeddings.
Yes.
You mentioned that it learns the initial embedding vectors. Yeah, there's some, and then there's some empty space.
And this is filled while learning.
And that empty space is filled while learning.
Yeah. So basically, the models, the training of the model will fill in. Where is it? Will fill in. So if I take the token Dresden, right? In the token Dresden, there somewhere all the things about Dresden, Sachsen, Wiesbaden will all be there. And this binary stuff, right? This is made up. It's just the intuition that this is enough to encode 50 bits. In reality, we don't know. It's just a vector in the vector space. Nobody knows.
Excuse me. The question to understand that code is enough to start. Is enough to train everything.
It's a model. The code you showed. It's 200 something lines. It's a model. That's all it is.
And this code uses some libraries.
No. I mean, it uses random math in OS. It's Python. That's all.
But can you sense this presentation? It's a bit
So NanoSchnack is my model, which I trained over Christmas myself. I just wrote Python PyTorch code here. This is PyTorch. And it's not super long either. It's the same size basically, or even longer.
One more question. For
Yes.
example, we write the cat seat on the table.
Mm-hmm.
How model understand how many words to generate after?
You can, so what I talked about is pre-training. In pre-training, you take the internet, right, and train with it. Then there's a phase called post-training, and in post-training, you can teach the model, and the training is much shorter. You can teach the model to become not only completion, like everything we have seen is completion, right? If you ask, what is die Hauptstadt von Deutschland? That's my training data example. It's not completion to answer Berlin, right? This is already something like a chat style conversation. So you can train the model after pre-training, after you have done all the internet training. You can feed it with, like there are databases, there's a big one, a German one from Facebook, a data set where you have lots of conversations, like 2 persons, 2 characters doing conversation. And you train with that, and then you also inject, and I showed it very briefly, you are training special tokens, like those. And you put in an end of sentence token as well, and you train with that. And the model will then learn that eventually it should give you an end of sentence token. And you can even do things, there's something called reinforcement learning, it's also a big topic. You can teach it to get a big loss if it answers too long. And if you have a chatbot like ChatGPT, you don't want a book, right? You want like the paragraph or maybe the screen size of answer. They are training the model and basically giving it a, penalty for too long answers. So after pre-training, after it knows all the internet and all languages, they do this post-training to get it to the shape you want. Yeah.
So you mentioned you have like there is a one-to-one mapping between the number of heads and the number of transformer blocks, right? In your
yes, nearly. So it's called multi-head attention because on every layer here, here's a big, where's a small one here? So I didn't go too much into detail. Every transformer block is the neural network, like the one which has the maximum function. And most factual data is here. Like that Paris is a capital of France. It's mostly stored here. This is basically the factual knowledge.
Most number of parameters.
And you might have heard of mixture of experts, like modern models, they have experts which have special knowledge. This is just n times this part. And not all of them are used for your answer, for the response to your question. Most semantical things, like everything which correlates between words and so on, this is mostly here, right? And a transformer block is always attention plus one neural network. And then we have those transformer blocks n times, like 100 times for a modern model, 12 times in my case. And what I said here, multi-head means in every transformer you also have n different, in my case 128, I think. So you have multiple of them. They can all look on different things in sentences. One looks on colors, the other one looks on...
They don't have to be the same.
Exactly.
Number necessary.
The number is fixed. I mean, the number is a meta parameter, right? Yeah. I could change it just with a Python constant.
From an architecture point of view, that doesn't have to be like a.
Correct.
If you break the embedding vector, like if the semantic vector is too big, you want to break it. Like if you're talking about the tokens about football, it's not about politicians. So you don't want to train like football content on the data you have on politics.
I mean, it's generic, right? For the mixture of experts, maybe you can do something like that, yeah, if you train them. I don't know how they do that. Maybe they do some distinction, like you say. Like they feed in all the football data, and then they all...
Exactly the MOE.
Yeah. But here in this, everything is uniform. There's nothing like that. And just for intuition about sizes, and I cannot go smaller. I hope I find that. Somewhere I have numbers. I'm not sure where it is. I think 60% or something is in the neural networks. CUDA codes. I don't see it. It's somewhere here. Hard to see. So 60% or something is in the neural network, and 30% is attention, and then there's some stuff around norms and biases, and what is also big is the token embeddings, like 32,000 tokens times the length of the vector. So you can do the math, right? 768 dimensions, real numbers. And 32,000 in a table, so you have many numbers just for that. And this is a training of embeddings, right? They are part of the parameters, the weights.
At the beginning, you said this nano-shack has 2 billion parameters, right?
Has what?
2 billion parameters?
No, this is 110 million.
110 million.
Yeah, this is like GPT-2, like the 2019.
RAM
huh?
does it need to be served?
This depends on how you serve it. Wait for Chris, he will talk about it. And the optimizations, you don't have to...
Just take the LLM, whatever. If you just want to serve it...
I mean, 100 million times 4 bytes, if you take the naive representation, you can do the math, right? Something like that. It's not big. That's why we run 64, or we tried 64, then there was an OM. But 64 batches, right? We have basically 64 in parallel. So we have 80 gigabytes in this machine, so you can do the math, how much space is there and how. Yeah. All right. This is the first talk. And yeah, everything I talked about fits onto this slide. If you could read it.